Hello there, welcome to AP Calculus Lecture 3.5 where we're going to talk about horizontal and vertical asymptotes. So this is going to be the last lecture where we are helping to determine what our graphs look like through calculus. So you need to have this note sheet printed out and a highlighter ready to go. And I'm going to talk you through the notes, and then we're going to work a bunch of example problems. Okay, so horizontal asymptotes occur where the limit exists. Okay, so we're going to get an answer. Does not exist as x approaches infinity or negative infinity. So we're going to be taking a limit as x approaches infinity or negative infinity, and then a horizontal asymptote occurs when you get an answer. If the limit does not exist, then there's no horizontal asymptote. So we take the limit of a function as x approaches infinity. So we actually did this in pre-cal. We didn't apply the calculus part, but to determine where a horizontal asymptote is, and of course it's always going to be a fraction. Your function's going to be a fraction, otherwise there's not going to be a horizontal asymptote. But if the highest power on top, so highest power like x squared, x cubed, we're talking about the exponent here. If the highest power on top is greater than the highest power on bottom, then the limit does not exist and there is no horizontal asymptote. So if the highest power on top is less than the highest power on bottom, then the limit as x approaches infinity is equal to 0, and we have a horizontal asymptote at y equals 0. Okay, that's just a line. That is the x-axis. Y equals 0 is just the x-axis. If the highest power on top is equal to the highest power on bottom, the limit exists and is determined by the coefficient. So when I work the examples, I'll show you what I mean if you've forgotten this from pre-cal. Now, we've already done vertical asymptotes but in Chapter 2, but I'm going to remind you, and we're going to do a couple of examples on these because you need to determine where the vertical asymptotes are to put them on the graph. So what we're going to, again, it's got to be a fraction. If the function is not a fraction, there's no vertical asymptote. So we're going to factor the numerator and the denominator, cancel where possible, and determine after you cancel, you determine where the denominator is equal to 0. It's all about where the denominator is equal to 0. Now, if one of the factors cancels out, that's on the bottom, there would be a hole instead of an asymptote. So we'll do an example that has one of those. All right, let's go. First of all, before I get going on doing examples, let's just draw a horizontal asymptote and a vertical asymptote. So a horizontal asymptote, we would just signify that by a dashed line. And our function will approach but just never touch that horizontal asymptote. All right, so we'll just call that a ha. And then a vertical asymptote, and of course you can have graphs that have both. Many, like if you look at the tangent function, it has an infinite number of vertical asymptotes. But here's an example of a vertical asymptote. We use it as a dashed line. And let's say we have a function that's going like this, and it just never quite crosses that vertical asymptote. Okay, so let's do some examples, and what we're going to do is find the horizontal asymptotes on these. And we're going to do it by taking the limit as x approaches infinity. So let's say we have the function 1 over x. So if you think about it, if you plug in infinity for x, 1 over infinity is just 0, right? So that limit is equal to 0. But another way to look at it is the bottom wins, the way we looked at it in pre-cal, because you have an x on bottom, no x on top, so the bottom wins. The highest power is on bottom. So we have a horizontal asymptote at y equal to 0. So the limit is 0, and there's a horizontal asymptote there. All right, let's look at the function. We'll take the limit as x approaches infinity of x cubed. Now that's just the same as x cubed over 1. So the highest power is on top, so the top wins. So this limit is infinity. So the limit is infinity. That just means it does not exist. So there is no horizontal asymptote. All right, let's take a look at the limit as x approaches infinity of 3x over 2x squared plus 1. Now, I don't care about the plus 1. I only care about the powers of x. And here, the powers of x, infinity, if you plug infinity in over infinity squared, right, the bottom wins. When the bottom wins, then the answer is 0. And when I say bottom wins, I mean the power is greater on bottom. So we have a horizontal asymptote, and on the homework, I want you to write this out at y equals 0. So at the x-axis, I'll do it with a different color here. That just means that on the x-axis we have a horizontal asymptote. So our curve will never pierce the x-axis there. All right, let's go with the limit as x approaches infinity of 5x cubed over negative 2x squared plus x minus 7. Now, looking at this, I just don't care about the x or the negative 7. It's only about the highest power. So only look at the highest powers. Okay, so here the top wins, right? So the answer is infinity. Infinity is just another way of saying does not exist. All right, so there is no horizontal asymptote. If it does not exist, there's no horizontal asymptote. All right, let's keep going with a few more examples for horizontal asymptotes. Our next example, so we're going to take the limit as x approaches infinity of 3x plus 1 over 2x to the 4th plus 3x squared minus 7. Well, the top wins, doesn't it? So you can just eyeball this. Excuse me, the bottom wins. When the bottom wins, x to the fourth is greater than x to the first. I don't care about all this extraneous stuff. I don't care about the 1 and about these. Only about the highest powers. So the bottom wins. So the answer is 0 because the bottom wins. So we have a horizontal asymptote at y equals 0. I want you to write the answer out this way. Don't just circle 0. All right. So let's take one. The limit as x approaches infinity of x squared. So it's time to change the game just a little. Plus x minus 6 over 3x squared minus 9. Now, we're determining the horizontal asymptote here, so we don't have to factor things and figure out where the bottom is 0 and factor the top. You're just looking at the highest powers. So if I just look at the highest powers, I don't care about x minus 6, I don't care about minus 9, it's just x squared over 3x squared. Okay, so if there's a tie in the powers, you use the coefficients. We're just going to mark out the x squared, and the answer then is 1/3. So we have a horizontal asymptote at y equals 1/3. So just a little bit above the x-axis, we have a horizontal dashed line. All right, let's take the limit as x approaches infinity of 97x minus 3x squared plus 4 over 1,000 plus 20,000 root x. So there is a lot of extraneous information here. But all I care about is the highest power. The highest power on top is x squared. The highest power on bottom is root x, or x to the 1/2. Okay, so the top wins, right? So do we have a horizontal asymptote? Okay, the answer to this limit is infinity. When the top wins, the answer is infinity. Actually, it's going to be negative infinity, so I apologize for that. Negative infinity, because we have negative 3x squared, so we haven't really dealt with a negative yet, over positive 20,000 root x. The negative would make it negative infinity, but that still does not exist. So there is no horizontal asymptote. So this is the first one where we've had a negative sign, and we've needed to look at that. I believe, anyway, this first one. So let me do another one real quick. I may have already done this one, but 5x cubed over negative 2x squared plus x minus 7. I might have done that and already erased it. But this one, the answer, it doesn't exist. There is no horizontal asymptote. But because it's 5x cubed over negative 2x squared, the limit does approach negative infinity. There's still no horizontal asymptote, but the answer in the back of the book, the official answer, is negative infinity for that one. So go ahead and correct it. I don't remember if I did that example or not. I'm much more worried about, do you know where the horizontal asymptotes go and the vertical asymptotes? All right, let's do some examples from the book. So let's call this examples with radicals and trig. So I'm coming from the book on these. So example 18 on page 193, we are taking the limit as x approaches infinity of x over the square root of x squared plus 1. Now that's the same. I'm going to go ahead and, what is the square root? I only care about the largest powers. What's the square root of x squared? So the square root of x squared is just x, right? So this is the same as x over x. They have a tie. So the limit is equal to 1. The coefficient in front of each of these is 1. So 1 over 1 is 1. So we have a horizontal asymptote at y equals 1. All right, example 20. So we have the limit as, and we haven't done one of these yet, as x approaches negative infinity, and you'll probably have at least 1 or 2 homeworks where it looks like that. Let's say we have negative 3x plus 1 over the square root of x squared plus x. Okay, so make a note here. When x approaches negative infinity, we must put a negative sign in front of the radical. Okay, so I only care about the highest powers here. So I've got negative 3x over the negative square root of x squared. Right, and we have that negative sign that I said you had to put in. That's just going to be negative 3x over negative x. There's a tie in powers, and so the answer is 3. So we have a horizontal asymptote at at y equals 3. So be careful and make sure if you have a negative in front of the infinity and you have a radical, you have to do that. All right, I think I can, let's go ahead and erase. Couple more examples from the horizontal asymptote problem. So 22, we're going to take the limit as x approaches infinity of x minus cosine x over x. Now if you look at your unit circle, cosine x just, and the same would be true of sine, it just oscillates between -1 and 1. The smallest it'll be is -1. The largest it'll be is 1. So really we can just completely discount the cosine x because 1 and -1, that doesn't compare to infinity. So this is just, the cosine x is kind of like one of those extraneous variables that's a smaller power. So x approaches infinity of x over x, right? It's a tie. So the coefficients tell me that's 1. So we have a ha at y equals 1. All right, and finally, the limit as 1 over x. Now, 1 over infinity, that's basically 0, right? This is the same as sine 0, which is just equal to 1. Excuse me, 0. Right? So we have the answer is 0, and we have a horizontal asymptote at y equals 0. All right, so the sine of 0 is 0. Think of 1 over infinity is just the same. It's a tiny, tiny number, right? So it's approximately 0. All right, so that is enough horizontal, probably more than you needed, horizontal asymptote examples. Let's just do, even though you've done this before, just to remind you how to do a vertical asymptote. All right, let's do our first example. In fact, let's title this VA examples. So we want to find the vertical asymptote on these. And our first one is f of x. So you don't take the limit here, is equal to 1 over x. So it's all about the denominator. So denominator is 0 at x equals 0. So we have a vertical asymptote at x equals 0. So that's the y-axis. In this particular case, the y-axis is where we would have a dashed line. So our curve can never cross over the y-axis. So you might have something like a function that looks like that. Something like that, and like that. Okay, next example. We have y is equal to x minus 2 over x minus 3. So where's the denominator? 0. And nothing will cancel out here. So this is really easy. We have a vertical asymptote at x equals 3 because that makes the denominator 0 and it doesn't cancel out. Now let's do one where you do have to factor. So you have y equals x squared plus x minus 6 over x squared minus 9. Now you know what makes the denominator 0 would be plus or minus 3, but one of those could be a whole. So let's see. We know that's the difference of two perfect squares, so it factors into x plus 3 times x minus 3. Here we have x. How about plus 3 minus 2? Would work. And then those cancel. So what makes this parenthesis 0, x equals negative 3, is a whole because it canceled out. However, x equals 3 is a vertical asymptote because it did not cancel. All right, hopefully you remembered that from, our chapter 2 lectures. All right, let's talk about the homework. We'll look at it in the book. And my instructions are a little bit different than the book's instructions. So I hope you watch this. So our homework is page 193. do 11 through 23 odd. And for those, you need to take the limit. So I want you to write it as, find the horizontal asymptote if it exists. So I want you to write the answer in terms of we have a horizontal asymptote at y equals whatever. So you take the limit, you get an answer, and if you get an answer other than does not exist, you have a horizontal asymptote. All right, that's for 11 through 23. That's all about the horizontal asymptote. 35 through 51 odd. Okay, so for those, it tells you to do a whole lot of work I don't want you to do. I only want you to find the asymptotes. Don't go through that whole thing. So find and the back of the book should have this graphed, and then you can look at it and tell where the horizontal and vertical asymptotes are. But take the limit as x approaches infinity to find the horizontal asymptote, and then do what we just did to find the vertical asymptote, where you see where the zeros are in the denominator. All right, that's 35 through 51 odd, and then I want you to do 67. That is a word problem where you have average cost. So you had one of these in the last section. So find the limit of c bar as x approaches infinity. So you're going to have to plug that 0.5x plus 500 into this formula, and then take the limit as x approaches infinity of that and see what happens. All right, that'll do it for this lecture. We're getting close to the end of this section. It ends at 3.6, so I will talk to you next video.